This video looks at sections 7-3 through 7-6 of the 9th edition of Harris's Quantitative Chemical Analysis. So in these sections, we're going to be talking about looking at precipitation titration curves. So we've already talked a little bit about the precipitation titration, but we're going to talk a little bit more about it here. So let's imagine that we wanted to analyze a sample for iodide concentration. So we wanted to know how much iodide was in that sample. Well, we can make use of this reaction right here. So the reaction between silver and iodide to form a relatively insoluble ionic compound. In fact, very insoluble ionic compound. So this would be the precipitate. So this is our precipitation reaction. So that's why we call these precipitation titrations. Now, one way that we could do this is through something called a gravimetric analysis. So what we would do is add excess silver to precipitate all of the iodide. We would get this solid, and then we could filter off that solid, dry it, and weigh it to figure out the moles of iodide that were originally in our sample. So that's how we would do it using gravimetric analysis. Using a precipitation titration, another way that we could do this is that we could monitor the course of the reaction between the silver and the iodide. We keep dribbling in little bits of the silver until it is completely reacted with all of the iodide. And right at that point, the equivalence point, well, that would be our endpoint, which we hope is the equivalence point when we've added 1 mole of silver for every 1 mole of iodide that we have. Then the reaction would stop. And by measuring the volume or the amount of silver that we've added, we would be able to calculate using stoichiometry the amount of iodide and figuring out its concentration. So how much silver and how much iodide is in solution at any point is controlled by, to a large degree, the equilibrium constant for this reaction. So you'll remember that if we write this reaction in reverse so that these products were the reactants, so just swap the reactants and products, that's the solubility product constant that controls the equilibrium for that reaction. So we would be using KSP to think about how much silver and iodide might redissolve from this solid. So we oftentimes understand titrations by looking at something called a titration curve. So a titration curve is a curve that shows how the concentration of one of the reactants changes as you add different volumes of titrant. So the volume of the titrant goes on the x-axis. That's the thing that we're changing, and we're thinking about what is the concentration of one of the reactants in our solution. So in this case, we're going to look at the concentration of silver ion in our solution as we go through the titration. Now, because these concentrations change over many orders of magnitude, so an order of magnitude is just a power of 10. So for example, if we go from 0.1 to 0.01, we've gone down by a power of 10, right? So we just divide that first number, 0.1, by 10, you get 0.01, right? So oftentimes we want to represent those powers of 10. And one way to do that is to use a log plot, or what's called a semi-log plot. And in chemistry, we define these things called p-functions, because oftentimes our concentrations are really small, so our exponents are like 10 to the minus 2, 10 to the minus 3, 10 to the minus 6, and so we want to get rid of that minus sign. So we define a px function like this, where p is the negative log of the x concentration. So whatever x is. Typically, x is a chemical species, and so it would be the molarity of x. And so that's what's plotted here is PAG, or PAG+. So that would be the negative log of the silver ion concentration. So this is what's changing as we do our titration. So these numbers up here then are telling you about the power of 10 on the concentration. So a PAG of 12 means that the concentration of silver in this solution is 10 to the minus 12th molar, a very, very tiny concentration. If we're down here at this level, then we've got a concentration of silver that's 10 to the minus 2 molar, which is like 0.001 molar. So 10 to the minus 2 molar is pretty dilute, but it's not super, super dilute, right? So remember that high values of px indicate very, very low concentrations of x. And low concentrations, or low PAG values, indicate higher concentrations of X. So you might wonder, why is it that up here we have any silver concentration at all, right? So we've added silver, but not enough to completely react with all of the I minus, let's say. So why would there be any silver there at all? Well, it has to do with this equilibrium reaction, right? So some of the silver iodide solid will undergo this reverse reaction and redissolve into the solution a very little bit to give you a very tiny concentration of silver. So we want to look at why this curve has this particular shape and what it can tell us about the equivalence point and how to find the equivalence point in a titration. So let's think about the shape of the titration curve. So the shape of this titration curve, you know, if we kind of exaggerate it a little bit, it looks kind of like an S that's been kind of pulled out by the ends of the S. Mathematicians have a name for this kind of function. This is called a sigmoidal curve. So this kind of shape is what a mathematician would call sigmoidal. So the shape of the titration curve, it turns out that the equivalence point is the steepest point on the curve. So right here you see this cliff, right? It kind of is pretty level here, and then we fall off the cliff down here, and then it levels off again. So this cliff face, this steepest part, that's where the equivalence point is. And we're often interested in measuring the equivalence point volume. And so that volume would be down here. So the equivalence point volume, sometimes we'll abbreviate that V with a little subscript E for equivalence point. So that's the equivalence point, typically what we're looking for. And so that happens where we have this steepest slope. Another thing that's going on here mathematically is that right at this point, we have something called an inflection point. And that's where this curve changes what we call concavity. So you may have heard about concave and convex. Well, we're thinking about concave shapes. And so we can have shapes that are concave up, where the bowl of the concaveness is sort of pointing up. So imagine cupping your hand and holding it with the palm up. That would be concave up. So if we turn that upside down, so that you're cupping your hand but holding your palm down, that would be what we call concave down. So if you look at the top part of this curve right here, it looks like a bowl that's upside down. So we would say that that is concave down. But if we look at the bottom part of the curve right here and trace this out, it looks kind of like a bowl that is right side up, right? With the bottom of the bowl sitting on the table. So we would say that that is concave up. And so at some point, we have changed from being concave down to concave up. So that's a change in concavity, and that happens at this mathematical point that we call an inflection point. So we can also talk about the sharpness of the equivalence point. So to chemists, sharpness relates to how tall this cliff face is. So the taller the cliff face is, the sharper or quicker your endpoint will be. It also relates a little bit to slope. So if you have a really steep curve here, that will be sharper than if you have sort of a curve that has some slope to it, like I'm tracing out here with my laser pointer. So if you have that kind of slope, less steep slope, then that's also a less sharp endpoint. So if we look here we have three different titration curves. One for titrating iodide with silver, one for titrating bromide with silver, and one for titrating chloride with silver. So looking at the iodide curve, you see that the cliff is really tall, right? So we got a lot of altitude here. So that would be the sharpest endpoint. The bromide is less tall, so this length, and the chloride is the least tall of all. So the chloride would have the least sharp endpoint. But still the slope is pretty steep right here, so it's still reasonably sharp as an endpoint. And so what we say is that the sharper the equivalence point, EP for equivalence point, the less soluble the precipitate is. So we can tell something about the solubility of these ions by looking at the KSP value, right? So the smaller this equilibrium constant, the more it's going to favor the reactants, right? And the reactants are the insoluble, undissolved material when we're thinking about those solubility product constant reactions. So 10 to the negative 17 is smaller than 10 to the negative 13. So iodide, silver iodide, is going to be less soluble than silver bromide with a KSP of 10 to the minus 13, which is less soluble than silver chloride with a KSP of 10 to the minus 10th. So those of you, if we're thinking about slopes here, the steepest slope, the point where you have the steepest slope, again, that's our equivalence point. That's what we're looking for. If you've had a little bit of calculus or plan on taking a little bit of calculus, there you'll learn about something called the derivative. The first derivative is just the slope of the line tangent to your curve at any point. So right at this point, our curve is really, really steep. And at that point, the steepest slope is going to be where the first derivative is the greatest. So we're looking for the maximum in the first derivative. An inflection point where we change concavity happens where the second derivative is equal to 0. So this thing right here is called the second derivative, and it's basically the slope of the slope. So if you were to plot out the slope at every point and then find the slope at every one of those points, you'd be looking at the second derivative of the curve. But anyway, we can do these sort of plots on a computer with our data that we've collected from titrations and use that to help us find the equivalence point, because it's where the curve crosses 0 and goes from being positive to negative or negative to positive, depending on whether you start up or down. All right, so it is actually possible, and we want to do this, to be able to understand the shape of the titration curve. We can use our equilibrium calculations to actually calculate and predict the shape of a titration curve. And so we're going to do that here and talk about that. But first, let's talk qualitatively about what's going on at these different regions in the titration curve. So we're going to talk about 3 different regions in the titration curve. Before we've gotten to the equivalence point, so V sub E, remember that's our equivalence point volume. So we've not yet added enough titrant to react with all the moles of our analyte that are in solution. The second region that we want to look at is at the equivalence point, so that point V sub E, when we've added exactly the right amount of titrant to react with all of the moles of our analyte. And then we want to think about what's going on after the equivalence point. So just in terms of a graph right here, this first part, we are before the equivalence point. Right at this volume right here, we are at the equivalence point, and any volume past this in this blue region, we're past the equivalence point, right? So what's going on at each of these points? So before the equivalence point, in our solution, we have excess analyte, okay? So maybe our chloride or our iodide we're thinking about. So we've still got some iodide floating around in our solution. So what is going to be the concentration of the silver in that solution? Well, we can find the concentration of our excess analyte by using this formula. So what we want to do is figure out the fraction of analyte that remains, right? So we're going to use up all of our analyte in the titration, but before the equivalence point, we've only used up a fraction of it. So like 10% or 50% or 89.9%. So we want to figure out what that fraction is. And if you multiply that times the original concentration of your analyte, so whatever the original concentration of the analyte was in the solution before you started doing the titration, that's what we want to know there. So again, if we've got an unknown solution of our analyte, generally that's what we're trying to figure out, so we don't know what that is. But right now we're just trying to think about, could we predict if we knew the shape of a titration curve? And then the last thing that we have to do is we have to multiply by a dilution factor, right? So we don't have the same volume of solution that we did originally because we've added some titrant to it already, right? So we may have added a little bit, like 10 mils, which isn't quite to the equivalence point yet. And so now we've diluted that solution a little bit. So we need to multiply by a dilution factor to account for that. Then once we know the concentration of our excess analyte, we can just plug that into our KSP expression to calculate the concentration of the silver ion. So that's how we would do things before the equivalence point. At the equivalence point, so right at this point, right here, we have added exactly enough silver to react with all of the iodide. So everything is precipitated. So what's going on then is all of the silver has reacted with all of the iodide, and now we've got silver iodide. And so a little bit of that will undergo this back reaction, and so we'll get a little bit of silver and a little bit of iodide back floating around in our solution. So just a tiny amount for whatever of this solid redissolves, okay? And what we know is that for every mole of iodide that appears in our solution, we'll have 1 mole of silver. So those two concentrations have to be equal. So that's what's going on at the equivalence point here. We've added just enough moles of silver to react with all the moles of iodide, so their concentrations are going to be exactly equivalent, and that's because of that solid silver iodide redissolving a tiny little bit into our solution. All right, so let's actually put this into practice. So for purposes of this course, I'm not going to expect you to be able to repeat these calculations, so I won't be testing you on this. But I want to walk through and show you that it can be done and that we can, in fact, explain the shape of these titration curves. By the way, it is possible to directly measure one of these titration curves using, for example, an electrode that's sensitive to the silver ion concentration. We could get a computer program to actually plot out the negative log of the silver ion concentration as we do the titration. So we can actually measure these curves experimentally. So let's talk about how we would do this. So we want to be able to calculate PAG, that's our y-axis value, when we've added different volumes of titrant. So what we're going to be doing is we're going to be putting 25 milliliters of 0.1 molar potassium iodide into the flask that we're titrating into. Our titrant, so what we're titrating with, is going to be silver nitrate. So this is the stuff that goes in our burette. And we're going to use 0.050 molar silver nitrate as our titrant. And we want to figure out what is the PAG after the following amounts of titrant have been added. So first off, we want to figure it out at the equivalence point. So what's going to be the PAG at the equivalence point volume? And then what's the PAG when we've only added 10 milliliters of silver nitrate? And what's the PAG after we've added 60 milliliters of silver nitrate from our burette? So our first step, let's figure out what the equivalence point volume is. So we're going to find what that equivalence point volume is, and then we're going to figure out, so we need to figure out this volume so we know whether we're before, at, or after the equivalence point. So we're going to find that first, and then we need to find the PAG value there. All right, so first things first, we know at the equivalence point that we've added just enough moles of silver nitrate to react with all of the moles of iodide that were in our solution. So those two have to be equal. Moles of silver equals moles of iodide. Why is it that way? We have to go back and look at our reaction, and you see from our reaction that it's a 1-to-1 stoichiometry. Now for other precipitations, you might have a different stoichiometry, but this is 1-to-1. So when we've added the same number of moles of silver that we have iodide, we have reached the equivalence point. So, knowing that those moles are equal, let's set up an equation to calculate those millimoles. So, how would we figure out the millimoles of silver that we've added? Well, we would take the equivalence point volume, VE, and we would multiply that times the molarity of the silver, 0.050 molar. So it's written here in millimoles per milliliter. So volume times molarity gives you moles, right? So if we knew the equivalence point volume, we would just multiply those. What about for the potassium iodide? Well, here we know we took 25 milliliters of potassium iodide, and we know what its molarity is. So volume times molarity gives you moles. And if we look at this equation, we've got one unknown, V sub E, in this equation. So what we're going to do to solve for V sub E, our unknown, we're going to divide both sides of this equation by 0.050. So we're going to take 25, multiply it by 0.1, and divide that by 0.05. And we will get this value for our equivalence point volume. So if we go back and look at our graph, you'll see right there at 50 milliliters, that's where our equivalence point is. So basically we're doing this titration up here where we've got 0.1 molar iodide that we're titrating, right? And it's going to be this curve. So while we're here, let's just talk a little bit about how titration curves change as the concentration of your analyte goes down. So here's the titration curve for a 0.01 molar iodide solution, and here's a 0.001 molar iodide solution. So you see our cliff is getting less and less tall the more and more dilute our solutions get. So that's kind of a problem with titrations, is they're not a good method to use if you're doing like trace analysis. So a trace analysis is when you have very little of your analyte in the solution. And the reason is that this cliff face is just so small that you wouldn't be able to see it. So titrations are good the more concentrated our analyte is in solution. Okay, so now we found our equivalence point volume. So now we are ready to figure out what the PAG is when we've added 50 milliliters of our silver nitrate titrant. So here we go. Let's think about what's going on. At the equivalence point, all of the iodide has precipitated as silver iodide solid. So the only way we're going to get any silver in our solution is because of this reaction, right? So we know about this reaction. This is the dissolution reaction. Solid silver iodide redissolves to give us a little bit of silver and a little bit of iodide. And this equilibrium is governed by the KSP equilibrium constant for silver iodide. And you can look these up in the back of your textbook for all kinds of different substances. And it turns out that the KSP for silver iodide is 8.3 times 10 to the minus 17. And so writing down the equilibrium constant expression, that's going to be equal to the silver ion concentration times the I minus concentration. So we see from this equilibrium that if we just have silver solid, that the moles of silver will equal the moles of iodide. So because those two concentrations are equal, we can just replace the I minus concentration with the silver concentration, right? It's like saying we've got X times X, and so we get X squared here. So KSP then is going to be equal to the silver ion concentration at equilibrium squared. So then we solve this equation for that silver ion concentration, and to do that, we just take the square root of both sides of the equation. So the square root of silver squared gives me the silver ion concentration. We take the square root of KSP. That will also, by the way, be equal to the iodide concentration. So we take the square root of that number, we get 9.1 times 10 to the negative 9th molar. So the silver concentration is, as we expected, very small. To find the PAG then, we just take the negative log of that number. So you take the logarithm of this number, and then you multiply that by -1, and you'll get 8.04. So if we go back to our plot here, where it tells us where the equivalence point is for all of these titrations with different concentrations, again, we're doing 0.1, you'll see that we're, right about at 8. So we were able to successfully calculate the experimental equivalence point, PAG. So at 50 mils, we've exactly reacted all of our silver, exactly precipitated all of our iodide, and our PAG will be 8. So now we're ready to do the next one. So before the equivalence point, when we've added just 10 milliliters, so we know the equivalence point is 50, so we're not yet there. All right, so before the equivalence point, right, we've not yet added enough silver to react with all of the iodide. We still will have made maybe a little bit of the silver solid, so the reverse reaction can happen and a little bit of that can dissolve, so we will have a little bit of silver in our solution. But remember, we've got this common ion here, so the iodide is actually going to shift the equilibrium to favor the products. So we're going to have even less silver than we did at the equivalence point. Remember, that's called the common ion effect. So at 10 milliliters, remember we've got excess iodide. Iodide is our analyte. We're still going to be using this KSP expression, and it will let us calculate the silver concentration if we know what is the I minus concentration at that time. So that's what we can calculate. So before the equivalence point, we've got a certain amount of iodide, and we've added 10 milliliters of 50, right? So we've added 10 milliliters of silver of the 50 that we're going to add, which will react all of the iodide. So we've reacted 10/50ths of the iodide that is present in the solution. So that means we can simplify this fraction so that it's 1/5, just dividing numerator and denominator by 10. So that means we've got 1/5 of the original iodide solution, of the original iodide, has reacted. So how much is left over? Well, 4/5. So we've got 4/5 of the original iodide. So what we need to do is multiply the original amount of iodide that we had by 4/5. The other thing that we need to do is account for the fact that now our volume has changed, right? So the concentration of iodide is going to change because we've diluted the solution. We started out with 25 milliliters, but now we've added 10 milliliters. So we've got a bigger volume of solution. So all of that is shown here as different parts. So what is the equilibrium iodide concentration? Well, it's 4/5. That's the fraction of iodide remaining that we just figured out. We're going to multiply that by the original iodide concentration, 0.1 molar. And then we're going to multiply this by something called the dilution factor. So we originally had 25 milliliters, but now the total volume of our solution is 35 milliliters. So if we divide the 25 by 35, that's what we call a dilution factor. And so when we do the math here, we will end up with the iodide concentration is no longer 0.1. It's gone down because we've added some silver. It is now 0.0571. So not a significant figure here, but we'll keep that for our later calculations. So now we're going to use our KSP equilibrium expression right here, and we're going to solve it for the silver ion concentration. So silver is equal to KSP divided by the I minus concentration. So we know what the I minus concentration is. We know what KSP is. So we just take KSP, 8.3 times 10 to the negative 17th, and we divide it by the I minus concentration, 0.0571 molar. And we get this number for the silver ion concentration. We take the negative log of this number and we get 14.84. Remember, that corresponds to this very, very small silver ion concentration. And if we go back to our experimental curve, you see at 10 milliliters, we have a number that is pretty darn close to 15. So 14.8 makes sense. So we have correctly calculated the value. And we could do that at any point along this titration curve. So as we have less and less iodide in our solution as we move closer and closer to the equivalence point, that common ion effect is less and less of a big deal. It still suppresses the silver concentration, but that's why our silver concentration is getting higher as we go this way. And then boom, we fall off the cliff because a small amount of volume causes a big change in concentration. We fall off that cliff and we get to the equivalence point. Okay, finally, let's think about what happens past the equivalence point. So past the equivalence point, we've added some extra silver ion from our silver nitrate that's in the burette. So we have more silver ion in the solution than we needed. So what we're going to first do is calculate how much extra did we add. Well, we only needed to add 50 milliliters to get to our equivalence point. That's our equivalence point volume. But we've added 60. So 60 minus 50 is 10 milliliters. So we've added 10 milliliters of excess. So now what we want to do is figure out the concentration of silver due to that excess. So what we're going to do is multiply by our dilution factor. So this 10 milliliters of excess silver nitrate is then diluted in the total volume of our solution. All right, so what is the total volume of our solution? We started out with 25, right, milliliters, and we have now added 60. So 60 plus 25 gives me 85. So the 10 excess divided by the 85 gives me my dilution factor. And then we're going to multiply by the molarity of our titrant. So we know what the molarity of our titrant is. It's 0.05 molar silver nitrate. So we multiply that by the dilution factor. So basically this is just a dilution equation problem, okay, taking the volumes and so forth and solving for the silver ion concentration. So 0.00588 molar. We take the negative log of that, we get 2.23. And so if we look back at our graph, we see down here at 60 milliliters, we do in fact have a PAG that's a little bit bigger than 2. So 2.23 agrees with the experimental curve. So by using all this math and thinking about equilibrium constants, we can actually predict the shape of titration curves and explain why they have the shape that they do. So what's important then is the steepness of this titration curve. That's a big physical change in our solution. So one of these concentrations is changing. So what we hope is that we can come up with a way of detecting that change. And I told you already that an electrode that's sensitive to silver might be one way that we could do that. A silver ion sensitive electrode, ion selective electrode, could do that. But there are other ways too that we're going to talk about. So we want to be able to sense that big change in these concentrations. So here the concentration doesn't change very much, here it doesn't change very much, but here at the cliff there's that big change. And hopefully that's something that we can detect as we're doing the titration. Okay, so it is also possible sometimes to do precipitation titrations of mixtures. So let's imagine that you've got two analytes, two ions that you're titrating, and both of them can be precipitated by your titrant. And so what happens is that the less soluble ion is precipitated first, and then you precipitate the next ion. And maybe there are more than two. So this only really works if the solubilities are sufficiently different. So if their KSP values are pretty different, usually by a factor of 1,000 or so. So they have to be different in the exponents by about 3 or more. So let's think about, so if they are sufficiently different, then what happens is the first precipitation is pretty much done before the second one starts. In that case, it's pretty easy to see where these two separate equivalence points are. So let's imagine that we're titrating a solution that contains both potassium iodide and potassium chloride, and we don't know what the molarities of those two things are. So we would like to figure out, well, what was the molarity of the iodide and what was the molarity of the chloride? So how much of each of these do we have in the solution? So we know that both of these precipitate when you add silver nitrate. And because the KSP equilibrium constants are very different for these two substances, silver iodide will precipitate first. So once we've added enough silver to pretty much precipitate all the iodide, then the concentration of silver abruptly increases because we're adding silver that isn't reacting with anything from our burette, and it immediately starts to react and precipitate the silver chloride. And then when all the chloride is consumed, we get another big increase in the silver ion concentration because now we're adding that excess silver ion. So the graph looks sort of like this. So graph B here is just titrating the iodide like we've sort of looked at before. And graph A here is when we've got a mixture of potassium iodide and potassium chloride. So what's going on here in the titration curve, these points right here that we've measured experimentally, is that, and so we're measuring the millivolts of some sort of electrode here that's sensitive to the silver ion concentration that's left in solution. So again, we see a cliff face that we fall down, and right at this point, we will have precipitated, so somewhere in here is our equivalence point volume for the iodide. And then, after we've precipitated all the iodide, we begin to precipitate the silver chloride, and we get to the equivalence point right here for the silver chloride. So we have to do a little bit of blowing this up and a little bit of funny extrapolation here to actually figure out the iodide endpoint, but it's at 23.85 milliliters, basically where this curve is flattening out right at this cliff face. And then we can figure out the chloride endpoint at 47.41 milliliters. And so knowing both of those milliliter volumes, we can use the first volume here to figure out the moles of iodide. And then we need to use this excess volume. So the difference between 47.41 and 23.85, that will, 23.85, that will tell us how much extra silver we needed to add to precipitate all the chloride. And from that information, we could figure out the moles of chloride. So the big upshot in this picture is that it is possible to titrate mixtures. And when you do that, you will see two equivalence points. So two of these cliffs in your titration curve graph, as long as the KSPs are sufficiently different. All right, so how do we go about detecting endpoints? So we're going to talk about two ways that we can detect endpoints. So we're going to look specifically at what we call argentometric titrations. So argentum is the Latin word for silver, and that's where we get the symbol for the element silver. And so anytime we're using silver nitrate as our titrant, we call those kind of titrations argentometric. Argentometric, fun word to say. Argentometric titrations. So we're going to look at two different methods. So the first method that we're going to look at is one called the Volhard method. And it's actually a back titration method. So what we're going to do is add excess standardized silver nitrate. So standard again means that we know what the concentration is. And we're going to add it to the unknown anion solution. And we're going to get a precipitate. Now, typically we will need to filter that precipitate off. And then what we're left with is a solution that has some excess silver nitrate. And so what we're going to do is back titrate those silver ions, that's from the excess that we added, using a standardized solution of potassium thiocyanate, KSCN. So SCN is a polyatomic ion with a -1 charge, so we have to add 1 K plus to neutralize that charge. And so we make a solution out of this stuff. We can find this in high-grade reagent, primary standard grade reagent, and mix that up. And we're going to do that in the presence of a little bit of iron 3+ cation. So when we're titrating, after all of the silver has been consumed, what happens is we form a complex ion because the SCN reacts with the iron. So first, the SCN is going to react with the silver to make silver thiocyanate. And after all that has reacted, then the excess SCN reacts with the iron to form a complex ion that gives us a red color. And so our red color tells us when to stop this titration. And like all back titrations, this will tell us the moles of silver that were left over from our reaction. And if we know how much we added initially, the difference between those will tell us how much reacted with our analyte anion. Okay, so that's the Volhard method. So again, here's how that works. So it's used in a back titration. Fe3+ is kind of the indicator. We have to do this in acidic conditions to keep the iron in the Fe3+ state and to keep things reacting as they should. So the first thing that happens is the silver reacts with thiocyanate to precipitate insoluble silver thiocyanate. So your solution's going to get cloudy because of this. And then when we've consumed all of the silver that was in our solution, remember this is in our burette now. This is the stuff we're adding from our burette. So we're titrating this silver. So then that SCN, the thiocyanate anion, is going to react with the iron and form this complex ion, which has a red color. And so that red color signals that you should stop adding the thiocyanate. And from that, we're going to be able to calculate the excess moles of silver. So that's the Volhard titration. The next titration that we'll look at real quickly is the Phygen's titration. Phygen's uses a special kind of detection indicator called an adsorption indicator. So adsorption, as opposed to absorption with a B, means that stuff is sticking to a surface. So to be adsorbed means that you've stuck to the surface. So water gets absorbed into a sponge, but might stick onto the surface of a plant leaf or something like that. So adsorption is sticking to a surface. And so the most common indicator that we use for, say, a silver chloride, determining silver chloride, is one called dichlorofluorescein. So this dye is greenish yellow in solution, but when you've got enough silver chloride around in the right form and it binds to that silver chloride solid, it turns red. So that's pretty cool. So we're actually precipitating out our silver chloride, and then when we get to the right point so that we've precipitated it all, the dichlorofluorescein will bind to that surface and turn red. So the pH has to be controlled a little bit because the indicator is a weak acid, and you have to make sure it's in the right protonation state. All right, so we have to be careful about that. That's just an experimental design factor that we have to worry about a little bit. And the indicator color changes right after the equivalence point when the charged indicator is adsorbed onto the oppositely charged surface. So the endpoint is going to be right at, maybe slightly after that equivalence point. So yeah, so let's go in and take a look at how that works. So what's going on here is we have this dichlorofluorescein. So that's indicated, those molecules are indicated by these little rectangles up here, and they're floating around in our solution. And now before the equivalence point, we've got excess chloride. So down here is a silver chloride particle that we've formed. So there's our silver chloride solid. So we're precipitating out the silver chloride. Now the silver chloride, you'll remember, is made up of positively charged cations and negatively charged anions. But because we've got an excess of chloride, these chloride ions can kind of find their way down here and bump up next to a positive silver cation and maybe stick there for a little bit. They may come off too, but then they'll stick there for a little bit. And so what happens is that the surface of our silver chloride particles pick up a slight negative charge because of those negatively charged chlorides sort of attaching themselves to those silver cation sites at the surface of the silver chloride. Now, because the dichlorofluorescein has a negative charge when it's in acidic solution, the negative and negatives repel each other, and the dichlorofluorescein will not attach. Now, once we get to the equivalence point, after the equivalence point, we've got an excess of silver cations. So now what starts to happen is these silver cations are going to attach themselves near to chloride ions that are at the surface. And we end up with a little bit of a positive charge on the surface of the silver chloride. Remember, this is the silver chloride solid right here. Now, because plus likes minus, these dichlorofluorescein molecules can attach themselves to the surface of that silver chloride particle. And when they do, this whole mess gets kind of a pink-red color. And that's how you know you've gotten to your endpoint. So here are just pictures of that titration. They're a little bit blurry. I apologize for that. But you see the dichlorofluorescein is kind of this fluorescent green-yellow color in the solution. As we begin titrating, adding silver nitrate from our burette into our solution that contains an unknown amount of chloride, we precipitate the chloride, and so we get this white cloudy solid that is suspended in the solution. And then when we get right to our endpoint, now the dichlorofluorescein can bind to the silver particles and make it this red-pink color. And so we know to stop adding silver nitrate. So finally, let's just look at some applications of these two methods. So the Volhard method shown here at the top is useful for determining the unknown concentrations of any of these ions in solution, depending on how you do the particular procedure. But basically variations on the Volhard method here can determine any of these ions. So if you have a large amount of these ions and you want to know how much of these are in solution, the Volhard method might be a go-to method for you. The Phygen's method is good for these other ions that are listed here. And again, it talks a little bit about special things that you might have to do with this Phygen's method. So these are all variations on the Phygen's method, but variations on these techniques to determine these different ions. So one way that you could determine the zinc cation is to do this titration procedure, this Phygen's titration procedure that is described here. So these basically Phygen's methods. All right, so that concludes Chapter 7 of the Harris textbook.